Hi, today we're going to take a look at what we call the shell method for finding volumes of revolution. We've been talking about how to find volumes using a disk. The shell method is just another way that can help us to find volumes now without having to change variables. For example, if I want to revolve this function here about the y-axis and I want to calculate the volume, well, if I look at the domain, the region from A to B here, if I want to revolve this about the y-axis, I have two problems. One, I'm going to wind up with two integrals because I got this part underneath between here and where they intersect, and then I have the part where they intersect where it's going to be b minus whatever the function is going to be. Makes it much harder. Another reason what makes it really hard is I'd have to convert f of x into terms of y, and that just makes it more work for us. Well, what we have now to help us is what we call the shell method. Now the shell method is very simple. We sometimes call it the parallel method, and we'll talk more about that in just a moment, why we call it the parallel method. Okay, so how it works is instead of going perpendicular to the axis of revolution, in this case the y-axis, we're going to go parallel with it. So if my axis of revolution, which is the y-axis here, is vertical, I make my rectangle vertical. Now you know why we call it the parallel method, because it's going to be parallel. Now if I revolve this about the y-axis, we get a very thin line that's going to be revolved, like so. And you can kind of see that. What we wind up with is a hollowed out cylinder or a shell that looks kind of like this. We get a hollowed out cylinder or a shell, a very, very hollowed out. What we want to do is find the volume of the shell. Now be careful because it's not the volume of the inside, it's literally the volume of the shell. If you imagine it like a piece of paper being kind of folded in on itself, like so, like this. Okay? This is my shell. If I look on the inside, there's stuff on the inside. It's empty on the inside. So to find the volume of this shell, what we're going to do is we're going to cut the shell down the middle, like so, and we're going to unwrap it. So it winds up looking like a flat sheet of paper, a rectangular solid, a very skinny rectangular solid, like this. Now, this shell, it has a length, this has a height, and it has a width. And we're going to calculate those. Because this shell now becomes a rectangular prism, which is easy to find the volume. The question is, how do we find all of these pieces? And they all come from our graph up here. Well, the height is very simple. That's this part right here. There's our height. Well, that should look familiar to us from area under a curve. The height in this case is just the top minus the bottom. Now if it's in terms of y, right minus left. So the top of my function is f of x. The bottom is just 0. So therefore my height is just f of x. No. To get the width, very simple. I'm in terms of x, very skinny, dx. Now the length is the hard one. Now the length comes from when I unwrap this. This length becomes on top. That's the circumference of a circle. So 2 pi r. But we don't want r, we got to keep r in terms of x. So we're going to replace r with something. We got to find what the radius is. Well, you may recall that the radius is the distance from the rectangle that we just drew to the axis of revolution. So that's this distance. Here's my axis of revolution. There's my rectangle. That's r. So what's it going to equal? Well, I don't really quite know, because what's happening is this rectangle is moving right and left, and it's going to kind of fill it in. So what is r going to equal? It's just some arbitrary x value. We don't know what it is, so we just call it x. So the length then is just going to be 2 pi x. So the volume formula then is just 2 pi x times f of x times dx. and we cleaned up a little bit. We're going to change x. We're not going to keep it as x. We're going to keep it as a radius in terms of x. So we're going to write as 2 pi r of x times f of x dx. Well, that's the radius, or r is the radius. Now, that's for one rectangle, or one shell. We have a lot of shells, so we're going to integrate that from A to B. And that is how we find the volume using the shell method. So let's take a look at an example. Imagine, let's take the function y equals x squared on the domain 0 to 2 about the y-axis. And we want to find the volume. So if I set this up, I'm just going to draw my parabola, y equals x squared, right here, from 0 to 2. So this is the region I'm kind of looking the shade here. And I want to revolve it about the y-axis. There's my y-axis. I want to revolve about the y-axis. Now, could I use disks? Yeah, I could use the disk method. If I want to use the disk method, very simple, like so. But I wind up with a washer. But not only do I wind up with a washer, it has to be in terms of y. Now this one's not bad because we just get the square root of x, or square root of y. So my radius is just the square root of y. So that's not too bad to do. And I can even find the volume. The volume here is just pi times the square root of y squared dy. And I'm going to integrate that. Be careful, this is at the point 2, 4. So it goes from 0 to 4. And that'll give me my answer right there. But let's take a look at what we call the shell method. Using the shell method, what it says to do is it says instead of drawing your rectangle horizontal, perpendicular to the axis, we drop it vertical to the axis instead. Now what's nice about this, I don't have to convert to y. And if I revolve it, we get our shell. But remember, our shell is just some rectangle, like so. There it is. It's dx thick. To get the height of my shell, well, that's just the height of my rectangle from area under a curve. Yeah! Kinda neat, huh? Yeah. So that's just the area under my curve right there. Now I gotta focus it, try to be funny. Alright. So, now, I have to get the length as well, so don't forget all those. So to get the height, top minus bottom, it's just x squared minus 0. To get the length, we said it's 2 pi r, but be careful, 2 pi, we have to find r. That's r. Now remember, r is the distance, so it's going to be really, this is some x value, it's really x minus 0. We'll talk more about that in a minute. So we get 2 pi x. Finding my volume formula here, 2 pi x times x squared dx. Now that's for one shell. To get them all, I'm going to get 2 pi x cubed dx, and we would integrate that from, be careful in terms of x this time, from 0 to 2. See, follow your rectangle. My rectangle is going right to left, and that's it. Now, these are two different integrals, but you can check that, solve them both. You will get the same answer in both cases. So, let's take a look at an example when we don't revolve about, let's say, the y-axis, but it's still going to be vertical, okay? So let's take a look at another example here. Let's take a look at the function y equals x cubed about, let's say x cubed on the domain 0 to 2 about, let's revolve it about the line x equals negative 1. So the idea is the same here. I'm going to draw this out. X cubed, we know what that looks like. From 0 to 2 is the only part that I'm interested in. So there's the region I'm looking to revolve. And again, I'm going to revolve it about the y-axis. So what does my rule say to do? Well, because our axis of revolution is vertical, because our axis of revolution is vertical, and I'm in terms of x, I use shells. We'll talk more about that in a minute. Okay, I'll give you guys a little bit better idea of how to use which one. Okay, so I'm going to use a shell. What does the shell say to do? Go parallel. So the shell method tells me I need to be parallel to the axis of revolution. And there we go. Drawing a parallel, when I revolve it now, I'm going to get a shell. But remember, our shell is really a rectangle. Height, width is easy, dx. Length is just 2 pi r. Now to get the height, same thing, it's just going to be x cubed minus 0. So it's just x cubed. R is where it gets a little bit tricky. I'm now revolving it about the line x equals -1. So if I go to -1, I draw my axis of revolution. Sorry, we're not graphing out the y-axis. Sorry about that, messed that up. So we're revolving about the line x equals -1. This is r. Well, how do we get r in this case? Well, remember, this is just some x value. It's the distance between them. And that's pretty easy. You can probably do that in your head. The distance between x and the origin is just x. Go over one more unit, x plus 1. Or just right minus the left. Just the right minus the left. So we get x plus 1. So my length now is going to be 2 pi x plus 1. And now I just want to find the volume of the shape. 2 pi x plus 1 times the height, x cubed times dx. That finds the volume for one rectangle, for one shell. To get them all, I integrate that from 0 to 2. And then you just solve that. And this one's not too bad to solve. We can get v equals 2 pi, 0 to 2, what's that, x to the 4th plus x cubed dx. 2 pi, integrate 0 to 2, x to the 5th over 5 plus x to the 4th over 4. And we get 2 pi times, that's 32 over 5, plus, what's that, 16 over 4, which is 4. And don't worry about 0, it just goes to 0, units cubed. And I wouldn't even worry about simplifying something like that. Alright, so very easy to do shells. Now, one thing you like about shells, one thing we really like about shells, no holes. Like there's no holes, like we have in a washer method. Watch this. Now, what if I want to find the same region, but something like this? Let's revolve the region bounded by, let's take a look here, y equals x cubed and y equals, let's say, 8 on the domain 0 to 2, and we're still going to go about the line about x equals -1. Now, we're going to finish up this on part 2, so join us for part 2. It's suspense, okay? See you then.